That's a better way to look that one up, so.
Okay.
All right. Did the homework go okay? Did you guys get there? I had a couple questions on email or whatever. There was some things were confusing on that, so that's a little bit more design than what sometimes we do in class, so it's kind of pretty open-ended. Do y'all find a decent solution? Did it seem like it, or no? What did you find? What did you run into?
My life and procedure rates make no sense.
So life was
It was giant.
It was giant, okay.
4,140,000.
So you couldn't get it down to
No.
anything reasonable. Okay, so that's a situation there. It's not. We locked Landon out. There you go. Yep. So that was a situation where it's a really, really low power, so that's not necessarily surprising. So you design the minimum whatever you can, and it's like, okay, the life is way longer than it needs to be, so that's all you can do. You can't get any further than that. So you go as cheap as you can with the shivs, as small as you can, keep them as close and tight as somewhat reasonable, and which means almost no arc of contact on that little shiv. So it's a pretty good size difference between those two, wasn't there, in this design? So keep them close, the low arc of contact on there. The life is still high. So oh well, that's what it is. So that's what you gotta go with. So if you can't get her down, you can't get her down. So that's it. All right, so how far did you beat on it and then give up? So I didn't have anybody ask me about that. I was kind of surprised because I figured it was going to come out with the life really, really high on that. So, oh well, we're good. Whatever, we'll move on. We'll go from there. So, yeah. So what we'll do today, and again, we're recording just so you know that we gotta. I don't know how to say what's going on, so but I think most people will figure it out. But yeah, so we'll get some folks out. What I'm going to do, the exam, I mentioned that we would move the exam to a week from today. Let's push it back one more period to the following Monday. So I heard from a couple people, I see this relief, there's 447 or something like that next week as well. So, so we'll push it back one more day. So it'll be a week from this coming Monday. All right, that'll give us what I'll do. I don't have the homework together quite yet, but I thought I unlocked it. Come on. I thought I unlocked it. I relocked it. There you go. So I will get a homework on the other mechanical power transmission stuff, on the chains, power takeoff shafts. These we'll do an example today on the shear bolt design, pretty simple example. So we'll have that homework. You'll have a week to work on that, and that'll be in before the exam, so that we have some practice on stuff before we see the exam. So we'll do the exam next Monday. Okay, makes sense? We'll go from there. So that pushes us pretty late in the semester. So I'm not sure what we're going to do for the final exam yet. So what's happening on there? So. And I would be open to suggestions from the class if there's something that, some way that you want to handle that. Week after Thanksgiving just doesn't sound like a great idea for a lot of different reasons. So my other class has shown some interest, and I cannot initiate this on doing stuff earlier and, before you leave or something like that. So that can't, doesn't follow university rules, but the class initiates some things like that. We can do some examples there. So I'll leave it at that. You guys kind of think about that, think through it. If you can have some ideas there, I'm open to suggestions on that.
I have a class that's actually quote unquote, giving out the final before Thanksgiving, but it's not due.
Not due until after.
The 2 hour period.
Yeah. So I may do something like that. So we'll see how we handle that, and if you guys have. Like I say, if you have suggestions there, but the rules are pretty strict in terms of what I can do that last week of class. So I can't initiate some things like that, but some things that you guys can initiate some things, and if everybody's in agreement, we can do kind of what we want, and we'll move on and have a good Christmas break, right? So whatever. So I'll just drop that bomb, walk away from it, and edit that out of the video, so there's no record of that, but we'll do something like that. Okay? So that's the deal. So any questions before we launch into this. I'm going to wrap up a couple comments here to talk about all these power transmission techniques. Yeah, sorry about the camera thing there. So no questions? All right, so let's look at this. So we've kind of, there's quite a few things that we haven't talked about in class here that are on the videos and everything, and I just wanted to kind of take a couple minutes just to kind of wrap those up a bit and make sure that that we have an idea, make sure that we're all kind of on the same page, we're staying with it, staying with the content and everything, and have an idea what the expectations are. But we've kind of blown through this. We started the course, the semester with looking at engines and how on mobile equipment, that's the way we create the mechanical power, usually on a rotating shaft, and then how do we get that power to where we need it to be and in the form that we need it to be, you know, the right speed, the right torque, whatever going on. So, and that's why we went through all these other power transmission techniques. So of course we spent some time on fluid power, on V-belts, you know, we did that design there, the chain drives, you see, you got the videos and stuff on that. The power takeoff shafts with the universal joints and that kind of interesting thing that we can make a shaft go around the corner, sort of. It vibrates and wobbles a lot, but we can do that and make that happen. We didn't spend a lot of time on, well, we didn't spend any time on gears. We're not going to have time to get into a lot of things on gears. I may look a little bit of that at that next week and kind of look at just some real top high level view of some gear techniques and stuff like that. So maybe look at that real quickly next week. But those are the fundamental things there, and then couplings. And what we'll look at today are the overload safety devices. So primarily from here up, not necessarily on overload safety devices, but keep in mind, and this is the kind of things I want you to do. They were in the videos, we've kind of talked about them here, some of these things a little bit. Well, what in terms of efficiency, how do you compare these different things in terms of efficiency? So can you do that? Can you look at those and say, all right, which one's more efficient? Which one's less efficient? So what about flexibility in terms of, okay, speed variations, going around corners, that kind of stuff, you know, which one gives me more flexibility there? The controllability, that's the speed variations and everything. Which one will last the longest, you know, which one requires a lot of maintenance, those kind of things. All right, what about the environment? So ag environments, we're out in the dust and the dirt and the sun and the wind and all kind of bad environments, and so that's kind of an interesting challenge. And which one of these would be better for those kind of environments and stuff like that. And then ultimately safety too. So when you get to the end, which one are the safest? Okay, so those are things that I want to make sure that you've pulled out of the videos and all that kind of stuff, and if we have questions about that, we can dive into that a little bit deeper in here when we're together and kind of look at some of those issues, but make sure that those things are kind of on the forefront, because that's the kind of stuff that I would expect you to be able to articulate on an exam or something like that. Okay? So does that make sense, going through those? Any questions on that right now, looking at that? Before we do our shear bolt example today. So some of you are saying, yeah, I got to go back and watch those videos. I know, yeah, there's some of that going on. Getting the end of the semester, senioritis setting in, and all that kind of stuff. All right, so let's do an example. So we're going to do a shear bolt example. Where we do a design here. So here's the situation. So it's actually a coupler. So you look at that device up there, it could be considered a coupler. So that I've got two shafts that are coming together end to end, and I need to fasten those shafts together and connect them so that they'll run together. And so how, you know, that's one there. I've got basically two plates. One of those goes on either end of the shaft. You can see the shaft coming in from the left and the right. And there's two plates, and they will rotate relative to each other, but I've got all those holes in there, so I put those bolts in that thing, bolt that thing together, and that makes one turn relative to the other. Okay, so when we're talking about these shear bolts and shear devices, I want to have, they're like a fuse. So I need to have somewhere in my mechanical drive line, I always have to think about this, what is my critical part, you know, what's the part that's going to fail And how do I protect that thing, especially if it's an expensive part? I don't want expensive parts to be failing on the customer and they have to replace these expensive parts. So how do I protect that? And that's where we're building in these mechanical fuses. So it's like a fuse in electricity. I think we understand fuses in electricity, current gets too high, but we have the same kind of thing in mechanical system. If the torque gets too high, I want this thing to fail. I want that to fail. I want this to be my sacrificial element that's pretty cheap, that's pretty easy to replace, so that I don't damage something else in the driveline. Okay, makes sense? Pretty straightforward, right? So how do we design that? So here's the question. So let's do an example where let's just look at what torque this would fail at. So here's some dimensions of that coupler up there. So the bolt diameter, so if you look at all the bolts that are in this thing, each one of those bolts, and there's 8 of them, the way it's shown here, those bolts, the diameter of that bolt is 12 millimeters. So these are metric bolts. The shaft diameter that's coming into this thing is 3.5 centimeters. Like that. So that diameter, that shaft diameter coming in there is 3.5 centimeters. That's what that is. And then the radius from the shaft center here to the bolt center, so the radius from here out to where the center of the bolts are, that radius is 6 centimeters. So that's what we mean by those dimensions there, okay? So that's 6 centimeters. Make sense? Clear what's going on? So what I'm going to do is say, okay, you know, I want to protect this thing, so that thing's got 8 bolts in it. Let's take them all out but one, and then figure out what torque that thing would shear at. So when it would shear, well, how much torque would it take to shear that with one bolt in there? So I'm going to pull 7 of them things out, put 7 in the toolbox on the machine. Then when it shears, I've got something to replace it, you know, right? So how do we do that? So torque, it is equal to force times the distance, right? So radius and R times some force, some radius times some force. That's torque. So what do we got going on here? So the torque where that thing fails is the radius out to where the shear surface is, where that shear is happening. So it's a radius on that rotating member out to where it's happening. So in this case, it's out to where the bolt is, the bolt that is shearing, times the force that it takes to shear the bolt. Okay? So we've got that radius, you know, that's the 6 centimeters out to where the bolt is shearing. But how much force does it take to shear that bolt? So how do we measure that? Force. So radius times the force. So if I know something about, oh, this is going back to strength of materials. So if I know something about the shear stress of a bolt, you remember shear stress and tensile stress and yield and all that kind of, oh, here we go, yep. So the ultimate shear stress, S sub U, so that's the ultimate stress, the ultimate shear stress, that's where it actually fails. So yield stress is where it starts to, you know, have permanent deformation. The shear, the ultimate, is where it actually fails. So this is the ultimate shear stress, S sub U, the ultimate shear stress. That's where it will fail. That's where it's going to shear and the metal will fail. Okay? What's the units of a stress?
Force under area.
Force per unit area, right. So megapascals, you know, PSI, whatever, something, whatever unit you're in. So it's a force per unit area. So that ultimate shear stress is force per unit area. So how do I get force out of that? Multiply it by area, right? So it's times the area. Now the question is, what area do I do? What area do I use?
Area of the bolt.
Area of the bolt, right. That's what's shearing. So what is shearing? What is the surface that's shearing? It's that bolt. So how big is the bolt? I'm going to shear that bolt off. So look at the area of that bolt. So that's what I'm going to do. All right, so I can plug all that in except for the ultimate shear stress. So what do I pick for the ultimate shear stress? So for bolts. And here's a neat thing. We can start to look this up. And I should have opened my browser here in my... And I got this set up. And let's look up Bolt Depot. There's a place where I always go. A good website is boltdepot.com. So that's a good place to find a lot of stuff about bolts. You can look this up a lot of different places. But this is one that has some pretty neat charts in there and it's easy to find. So from Bolt Depot, I always go to fastener information up there. So there's fastener information. And scroll down under fastener information to fastener materials and grades, right there. Fastener materials and grades. And here we go. Bolt grade, markings, and strength chart. I should have brought some bolts up here to pass around today so we had some toys. I didn't think about that. Forgot about that. But this will tell us about different bolts. So you go pick up a bolt, and a lot of people don't realize that, especially we're out on the farm or something like that. You get a box of bolts, you just grab a bolt. If it's the right size, you put it in and go, and you don't think about there's a lot of different kinds of bolts out there. As engineers, we understand that, but we also need to think again, as we're designing machines, how's the customer going to be responding to this? What are they going to do if they have to replace some bolts and so forth? Okay, so there's two different standards that go on. One for metric bolts and one for the English or standard US bolts, US sizes, okay? So, the most common ones that you see, if you go to buy bolts, are, you look at the top of the head, you look at a bolt head, the top of the head, and it's either going to be clear, nothing on it, it's going to have 3 little tick marks like that, or it's going to have 8 tick marks on it, or yeah, not 8, 5 tick marks on it, okay? Don't ask me why it doesn't make sense, but yeah, great, this is nothing is a low or medium carbon steel. That's a really cheap bolt. These are probably more common than a lot, but this is what we call a grade 5 bolt. And this is a grade 8 bolt. So this is a harder bolt. Okay? And we've got some information for each of those. Make sure you can see the top of the, come on. See the top of that chart. So the mechanical properties of that chart. So it gives me the nominal size, gives me the proof load, gives me the minimum yield strength and the minimum tensile strength. So if somebody manufactures a bolt, they manufacture a bolt that is grade 5, then it has to at least, for the smaller bolts, it has to at least have a minimum yield strength of 92,000 psi. All right, so what's the difference between yield strength, tensile strength? Go back to strength of materials. What is the differences there? We talk about yield strength. We talk about tensile strength. What does that mean?
Yield strength is when it starts to deform, and tensile strength is when it breaks.
Yeah. So yield strength is when, I stretch it, any kind of metal I pull on, it's going to have some elasticity, right? Modulus of elasticity. So it's going to stretch, but it's going to go back. Unless I pull it hard enough that it goes beyond its yield strength, it's not going to fail, but it's going to have a permanent deformation in it. So yield strength gives me the permanent deformation, right? So the tensile strength then is I pulled it hard enough that it fails, it breaks. So that's the difference between those two. Okay, so tensile strength. The proof load then, any idea what a proof load would be? And it's a little bit less than that yield strength. So there's a buffer in there. What they do with bolt grades is they say, okay, if you stay below 85,000 psi, in this case, you're going to have no problems. Between 85,000 and 92,000, your guess is as good as anybody's. It depends on the manufacturing of the bolt, the day of the week, who was working there, what mood they were in, and all that kind of stuff when they built the bolt. But once you get above 92, it's pretty much guaranteed you're going to have some permanent deformation in it. So that's kind of what that means. So when you're designing stuff, if you want to be sure, you want to stay below the proof load, but you don't have any stretching, you don't have any permanent deformations in it. Okay? So that's how you would, in terms of design, that's how you would pick bolt sizes to make sure that you don't have problems. Now, we're interested in this thing shearing. Okay? So, and then part of the philosophy is, okay, I can have all these different bolts in my, in my pocket, in my arsenal. So as an engineer, I can design all these bolts. And so I'm going to design, I've got a situation where I need a really low strength bolt. I need that thing to shear really easily. And so I put this really soft bolt in there. And that's fantastic, and you know, the machine's out there, it shears, and the customer's like, oh crap, I gotta get my machine going again. So what do they go to the toolbox and pull out? They pull out whatever's in there, right? And so if they've got one of these, that's what they throw in. And maybe that one breaks, and then they say, okay, this is stupid, I'm gonna go and get one of these and stick it in. So what has happened to your design? Your design has gotten compromised because now they're putting stronger and stronger bolts in there, and when you're looking at it from a shear situation. So it's an interesting design dilemma to think about. So what a lot of manufacturers will do is make special size bolts, so they can't just go grab a normal bolt out of the box somewhere and have it work. So they have something with a shoulder on it or something like that. It's kind of a special bolt that says, okay, to replace this thing, you got to put this soft one in there so that it doesn't damage the machine. So there's some strategies like that that engineers will employ. Okay, that makes sense? So, sort of, but you got to think about, you know, that's part of the challenge, is think about how are the customers going to abuse my machine? What are they going to do to it? So this is what we think about it. All right, so what I'm going to do for my example, let's get back to my example. So we're going to go to metric grades, and in metric grades, it's somewhat similar, but they put a number on the top of it with the strength on there. So it's class 8.8, 10.9, 12.9. So if I'm in metric size of bolts, which I am, this is what you would pull off. So that's what those bolts will look like. And they're literally stamped on there. And I should have brought some in. I forgot to bring my bolts. I got a box of bolts to pass around. All right, so in our example, let's say that we're going to use a class 10.9, so the mid-grade bolt. So this is the one I'm using there, the 10.9. So what do I need to know? For my example, what do I need? Do I need the tensile strength? What do I really need? I need the shear strength. I don't have that, do I? And especially some specialty shear devices, they'll give you that, but with bolts, they don't necessarily do that. So there's that, remember Poisson ratio and all that kind of stuff from, oh, geez, you're making digging all this stuff out. All right, so let's pull off the tensile ratio. What we can do is make an estimate of what the shear stress, the ultimate shear stress is based on the ultimate tensile strength. The ultimate tensile strength for a class 8.8 bolt or a class 10.9 is what? 1040 megapascal. So let's go back over to my example now. And so my tensile strength, ultimate tensile strength, T sub U is 1040 megapascals. And what I can do then to get the ultimate shear stress is to take the tensile strength, the ultimate tensile strength, multiply that by Poisson's ratio. Typical is for steel is 0.6. So if we multiply it by 0.6, that'll get us pretty close to what the ultimate shear strength. So in our particular case, this is 1040 times 0.6 is 624 megapascals. So that'll give us an idea what that ultimate shear strength is. So now it's plug and chug, easy stuff. So the torque where it's going to fail is equal to the radius. Again, this is the radius of that rotating member out to the shear surface. So what radius do I use? Again, radius out to the shear surface. So from the center of the shaft out to the shear surface. What are we looking at there? Wake up and tell me. I want somebody to wake up. Do I use 3.5? Half of 3.5? It's the 6. So what's the shear surface? It's one of those bolts that's going to break off. So I'm going to break one of those bolts, and it's out, in this case, it's out that 6 centimeters, right? So the radius is, and I'll put it in meters, 0.06 meters over 1. So that the units cancel off, so I'm using 0.06 times the ultimate shear strength is what? Times 624 times 10 to the 6th newtons per square meter times the area. What area do I use? area do I use? What's shearing?
Area of the bolt.
The area of the bolt. So what is the area of the bolt? Diameter of the bolt, 12 millimeters. So times pi over 4 times the diameter squared. So diameter is 0.012 squared. That gives me square meters. Then, let's see, units cancel off, the meters are gone. I'm left with a newton and a meter in the denominator. Is that what I want? That's pretty much what torque is, right? Hey, so there we go. So the answer then is 4,230 newton meters. That's what it gives me. So that's the torque at which it would fail. Now most of the time when we're designing, we're going to have an idea of what torque we want it to fail at, and so we're going to back calculate what size bolt do I need to make sure it shears at that point. Okay, so that's the engineering, the design would just go backwards from that, but that's how I calculate it. Cool. All right, another example. We'll do one more. This is different. I'm going to try to draw, see how this goes. This usually doesn't go well. So same shaft, but different kind of mechanism, all right? So here's the deal. What I'm going to do is put it, this is a common way to do things, so I'm going to have a mechanism that looks something like this, all right? Like a shaft going inside another collar, looks something like that. And I'm going to put a bolt through it. So here's my bolt. It's going to go down through here like that. And I'm going to put a nut on the bottom of the bolt down here. And these are my threads on the end of the bolt. That's what we got. All right, yep, Ben?
For the last problem, why would your torque not be times 8?
Okay, I said I pulled all the bolts out except one. Good point. If I have more than one bolt in there, then I've got to multiply by a number of shear surfaces, and that's exactly what we're going to see here. Okay, so what Ben's going right to. So I wasn't clear on that. I mentioned that pretty quickly, blew by it. But yeah, if I had all 8 of those bolts in there, it'd have to shear all 8 of those bolts. So the torque when it shears is times 8, right? Absolutely. So in this particular situation, so again, what we got is a shaft, and it goes inside of a collar. And so this is the bolt that I'm going to put through. I'm going to want that to be my sacrificial bolt. So if that torque gets too high, I'm going to shear that bolt. I'm going to bust that bolt. All right. So how many shear surfaces do I have now? Kevin's putting up 2 fingers. Everybody agree with me, him on that? Yeah. So think about that. If this thing turns, how does it got to break? For it to turn, for it to break free, it's got to cut the bolt there. And it's got to cut it right there. So I have 2 shear surfaces where it has to break. All right, so it's the same kind of equation. So what torque does this one fail at? So let's say this is still a 3.5 centimeter shaft. 3.5 centimeter shaft, same size bolt, 12 millimeter bolt. So we're going to put a 12 millimeter bolt through there. Same kind of a deal. And what's the torque where it fails at? Let's calculate it. Torque is equal to, again, the equation is the radius times all of its shear strength times the area. Now, one thing I missed up above there was how many shear surfaces that I have. Okay, and what Ben pointed out, if I had all 8 of those bolts up in there, I'd have to take this equation and multiply it by 8. So whatever I did down here would be times 8. So in this particular case, I've got to multiply it by 2. So I'm going to put in here times, and I'll stick in an N for a number of shear surfaces. So maybe a capital N would be better. I don't know. The number of places where I got to cut the bolt. So that bolt comes out of there in 3 pieces when it comes out, and so it has to cut it twice. So let's run the numbers. Torque is equal to, what's the radius? What am I going to put in for the radius in this particular example? What do we say the radius was?
Center line of shear surface.
It's the center line of my rotation, the center of my rotation out to my shear surface. Okay, so up there the shear surface was one of those bolts that was arranged longitudinally with the shaft, so it's from the center of that rotating shaft out to where the bolt is. In this particular case, where am I going to? Going from the center of the shaft, right through here, out to this surface out here. So the radius is from here out to where the thing gets sheared off. Okay, does that make sense? Everybody clear on that? So out to wherever that thing is sheared. All right, so radius is, what do we say? 0.035 divided by 2. So it's 3.5 centimeter diameter shaft, so the radius is half of that. So 0.035 in meters divided by 2. With me on that? Times ultimate shear strength up above there, 624 times 10 to the 6th newtons per square meter. What's my area? That's a shear area. Wake up, man. Is this like too easy that everybody's just bored out of their skull, or pretty much maybe? I don't know what's going on. How do you get area? Pi over 4 times diameter squared. What's the diameter I put in there? How big is the bolt? Said it's a 12 millimeter bolt, just like we had up above there. So it's the same thing as what we did before. So 0.012 squared. And that gives me meters squared, all right? Got to multiply that by how many shear surfaces? We got to multiply that by 2, so we have 2 shear surfaces. You crank this one out, 2,470 Newton meters, all right? So interestingly enough, pretty similar drive situation, same size shaft and everything. So one 12 millimeter bolt in the configuration like we had up above there in that picture gives me a little over 4,000 Newton meters, but I have one bolt here in what we call a diametral shear configuration. So I got to shear it twice and it's a lot less. So that radius has a big deal to play in that, okay? Now, let me challenge you a little bit, blow your mind a little bit. This is really just an estimate, because what really is the surface area of that shear? Think about that for a second. Look at the circle, end view of the shaft, right? Bolts coming down through. Here's my surface area up there where I shear the bolt on top of it. Did I show you why it's not really correct? All right, so is that shearing it flat? No, it's shearing it in a circle. So if you have a situation where it's a fairly large diameter bolt and a fairly small diameter shaft, now I've got a curved surface here, so I'm not shearing this straight off, I'm shearing it in a curved surface. So that surface area, that area of the shear, is actually a little bit bigger than just the cross-sectional area of the bolt. Okay, so most of the time that's so minimal, that difference is so minimal that in terms of design, and really when it comes down to it, that shear stress was kind of a guess anyways. You know, that's kind of a little bit of a loose number, so you don't have to really split that hair necessarily to get into the right number, the right value that you need. But just something to kind of blow your mind and think about a little bit. But it really is not necessarily the area of the bolt, it's the area that is being sheared. So it's how much steel, how much material am I shearing off? That's the key thing. Okay, that area is being sheared. Does it make sense? Cool on that? Questions? Pretty straightforward. Kind of an easy design, but we'll give you some practice on that, on some homework. All right? Good enough. Man, easy day. Let you go a little early because I kept you a little late on Monday, right? So, there's no questions on anything. Have a good one, and we'll see you next week. Watch for that. I'll get that homework sent out here hopefully later today so that you can start working on that. A couple design problems for these mechanical power transmission devices. Put your homework in if you got it.